Video to go with the in-person lecture on either August 24th or 25th. I'm Mr. Olson. This is Algebra 2 Trig. Hopefully you have your notes out. If not, pause the video, go ahead and get your notes because I do want you taking notes along with all of these videos, and that's something that I can check for in class if I want to. In your notes, go ahead and put the date at the top, and everything I write here, I'd like you to write down your own notes. All of our problems, I want you practicing them on your own. Now in this video, questions are going to pop up. That's part of how you get credit for completing this video. The grades in the grade book are just going to be completion, so don't stress too much if you get one wrong. This is the first time you'll be seeing some of this information. But do your best. If you're missing a whole bunch of them, we'll have a conversation and see what's going on. If you're struggling or if you're not taking it seriously, hopefully that doesn't happen. Now is a good time to pause the video and look at our do now question, maybe even sketch this diagram in your notes, and see if you can figure this out. You bought a mobile kit. You read on the package that the weight of the entire mobile is 40 ounces. Each inch of crossbar weighs 1 ounce. What is the weight of each shape? All right. Let's go ahead and pause. So here's how I would figure this out. First time I looked at this, I thought, well, maybe we should go bottom up, but it's much more difficult to do it that way. In fact, we should go top down. So each of these vertical lines is a string, and the mobile is perfectly balanced at that point. That's why this crossbar is straight. So we can say if this whole thing is 40 ounces, that on this topmost string, all 40 ounces is suspended with 20 ounces on both sides. And now I can look at the simpler side over here and be able to figure out what this big orange shape is. The 4 inches of crossbar is going to weigh 4 ounces. That leaves only 16 ounces remaining. So this orange one has to be 16. Now we can keep using similar logic to get these other ones. All right, let's go to the other side. This whole side is 20 ounces, but we've used up 4 of those ounces for this crossbar here, meaning that hanging on this string is only 16 ounces, which is going to be split up into an 8 and 8. Well, we'll go with the simpler side here. This whole thing has to be 8. 2 more ounces get used up by this crossbar, meaning that this yellow one must be 6 ounces. All right, and if this side was 8, then this side over here must be 8. 2 more ounces get used up here, so we're down to 6 being suspended at this point. We get rid of another 2 for these 2 inches of crossbars, meaning that we're down to just 4 ounces. And since these are both green and identical, we can assume they weigh the same amount. So 4 ounces divided by 2 is 2 ounces each. And now, as a good double check, we go and we add everything back up. 1 ounce for each inch, and then the numbers that we've written on these shapes, and we should get back to 40. All right, so what we're doing here is we're solving equations. The equal sign in an equation is just like how all of these poles are balanced with the same amount of weight on each side. And we've got some unknowns, which are a lot like variables. All right, so our goal for today is to review the terminology surrounding solving equations, and especially what a variable is. Why we're doing this is so we can be able to communicate precisely about math, so I'll understand what you're saying about math, and so that you'll understand what I'm saying. All right, now here's a little disclaimer. I do this at the start of every first semester of Algebra 2 Trig that I've taught. And I just want to say that during this unit, we're going to be reviewing some major concepts from Algebra 1. Be patient if you think it seems really easy. Everyone's kind of at different spots. And there's going to be plenty of opportunities to push yourself further, and this class is going to get a lot harder. We just sort of have to pick everybody up where they're at as we go through our unit on linear functions and quadratics and into polynomials this semester. And I guarantee some of those topics in polynomials is going to challenge even the brightest of you. So hang in there. If you're bored, you won't be bored for long. All right. What makes something an algebraic expression? So in my mind, there's two things that make something an algebraic expression. One are terms, and the other are operations. Okay, let's take these apart. What is a term? Well, a term contains things like coefficients, variables. You can also get exponents in there. All right, and all of these things, the coefficient, the variables, and the exponents, they're all glued together, and they're glued together by multiplication. The coefficient is multiplying the variable, and the exponent represents repeated multiplication of the variable. But the glue is multiplication. I'm going to write that. The glue is multiplication. All right, terms are separated out by other operations. So multiplication counts as an operation. So terms can have operations within them, but there's other operations like adding and subtracting that helps us combine multiple terms. And there's also operations you can do to just a single term or even just a single value like a square root. So together, terms and operations make something an algebraic expression. Now there's something else that we can add in that will elevate an expression into an equation. So, all right, so if we add in an equal sign, just draw an equal sign, it makes it an equation. All right, so an equation uses an equal sign to join two expressions. Terms are joined by operations. Is there any other way to join two expressions other than an equal sign? We could do an inequality. We could do a less than, we could do a less than or equal to, we could do a greater than or equal to. These here, if we use these to join expressions, we're going to start calling them inequalities. So makes it an inequality. All right, so an inequality is joined by an inequality symbol. So we call these inequality symbols to kind of keep that separate. It's easy to just call these inequalities, but if we want to be really precise with our language, we need to add that word symbol in. Okay, the one word on here that I really want to focus in on is variable. So what is a variable? Here I'm going to put another spot for you to write to me everything you think a variable could be, everything you know about what a variable is. All right, now I want to go into my first metaphor for a variable, and here we've got the picture of a balance. And in this metaphor, a variable is an unknown that we want to solve for. It has a value, we just need to uncover it. And we uncover it by using inverse operations and the balancing method. So an inverse operation would be like taking away these three red circles from this side, and then the balancing method means that whatever we do to one side, we have to do to the other side. Now we've revealed that the x here was equal to 4 kilograms all along. All right, so sometimes a variable is a placeholder, but it's secretly a number that we just have to figure out what that number is. And if we get rid of the balance, we just represent everything with symbols, we create equations, and then we can solve those equations. Here we've got x plus 4 equals negative 12. I'm going to use the inverse operation of plus 4 minus 4 and the balancing method to reveal that x was equal to negative 16 all along. All right, and then you can plug it back in to double check. Negative 16 plus 4 is negative 12. Negative 12 equals negative 12. It checks out. Sometimes the variable shows up on both sides, and that's how we can start building up multi-step equations, equations that require that we use all of our different operations in math to be able to reveal what that variable was all along. So here we've got a number in front of a set of parentheses. That tells us we need to distribute that number. So now I've got negative 27 plus 6y equals 3y minus 9. I've got variables on both sides, so I'll use an inverse operation to bring them together by subtracting 3y from both sides. Negative 27 plus 3y equals negative 9. Constants on both sides, I always want to move my constants away from the variables. So now I get 3y equals 18. And now to get rid of the coefficient, I can divide it away. Y equals 6. Plug it back in to double check. This is the kind of stuff we're going to be practicing in class a whole bunch. We'll be going through lots of different solving techniques, all the different ways a multi-step equation can present itself. But let's move on. Another metaphor for variables would be as placeholders, but we don't ever have to uncover their value. So imagine yourself, you're driving a truck and you come to a bridge, and you want to know if your truck is going to fit on the bridge, but you don't want to just drive it out there, because if it doesn't, then you'll get stuck. So you don't have a tape measure, so you go wander off into the woods and you find this stick and you lay it across your truck and you fold it over and you see that your truck is 5 sticks wide, and then you go over to the bridge and you lay it down and you fold it end over end and you see that the bridge is 6 sticks wide. Well, now you can tell that your truck's going to fit, but you never had to figure out what the actual length of that stick was. You never had to assign a value here. So variables, we can do a lot of math with them without ever having to reveal their value. Like in this example here, what is the area of this shape? Well, we know area of a rectangle is length times width. Here the length is x centimeters, the width is 4 centimeters. Length times width would be 4 times x centimeters, or just 4x centimeters squared, because it's an area, so square centimeters. So I can express an area with a variable, don't ever have to reveal what that variable is. Let's try another example. What's the area of the combined shapes? I should have run of this combined shapes. So similar, we multiply these to get that this is 3x centimeters squared. Multiply these to find that this is 5x centimeters squared. Together they become 8x centimeters squared. They were combined like terms by adding together their coefficients. All right, another example. Go ahead and try this one. What's the volume of this prism? Volume, we know, is length times width times height. So I can multiply these 3 dimensions. And now we get that this is 4 times 7 times x, or 28x. Now it's centimeters cubed, cubic centimeters. We have centimeters appearing 3 times. And the cubic centimeter is a measure of volume. All right, another rectangular prism, so length times width times height, but one of them is x plus 2. So that makes things just a little bit harder. Go ahead, sketch this one, try it. So length times width times height, I'm going to do 3 times x times, then I'm going to use a set of parentheses to keep that x plus 2 together. Now I can rewrite this. I can drop those time symbols, just write this as 3x parentheses, x plus 2. But I'd like to get rid of those parentheses. It's not considered to be fully simplified until all the parentheses are gone, so I'm going to distribute in this 3x. Get 3x squared plus 6x if I do that multiplication correctly. And then we don't have a unit here, And when you don't have a unit in the problem, you still have to say that this is cubic units, so units cubed, whatever the unit is, the answer is that unit cubed. All right, here's one to challenge yourself with, where all three dimensions are these binomials. Let's go ahead and try this one. So we've got x plus 2, it's one of the dimensions. X minus 1 is another dimension. X plus 4 is another dimension. What I'm going to do to get rid of my parentheses is I need to complete the multiplication that's in between here. And I do that by foiling. So I can't combine like terms, so I have to just make sure that every term multiplies every other term. So I foil. Foil stands for first, outside, inside, last. And that helps me remember what order to multiply these in. So first, x times x, that's going to get me an x squared. Outside, x times a negative 1 gets me a minus x. Inside, I get a plus 2x. And last, I get a minus 2. All right, keep a set of parentheses around that because these two terms haven't been distributed into the last one yet, which is an x plus 4. I can do some combining like terms here and turn this into x squared plus x minus 2 when I combine that negative x and that positive 2x. And now I got to do this distribution. I can't use FOIL as my acronym because this has got 3 terms. Instead, I just have to make sure I go first to first, first to second, second to first, second to second, third to first, third to second, and I get every combination possible. So let's say I get an x cubed plus 4x squared plus x squared plus 4x minus 2x minus 8. I follow all of those arrows and now combine like terms to get our final expression for the volume here. X cubed plus 4x squared plus 2x minus 8. So here's an expression for the volume of this rectangular prism. We don't know what x is, but all of the lengths have an x in them, so they're all relative to x, and we can come up with this nice, very compact expression for the volume of this prism. We can do useful math with it, and if we ever do figure out what x is, we can quickly plug it into this expression down here and figure out the volume a little bit quicker than having to plug it in and then do all the multiplication again. All right, one last metaphor for a variable is as a lever, where it's not an unknown that's going to be solved for or an unknown that won't be solved for. It's an unknown that we are going to deliberately change to see how it affects the rest of the problem. One place we see this is with graphing. When I graph an equation like y equals 1/2 x plus 4, this equation has 2 variables in it, but neither of these are ever going to be solved for just a single number and then remain that number. What we can do though is we can plug different numbers in and see what happens. So x here is the lever for the problem and it's showing you what happens to y. So I can plug in a 0 here. 1/2 of 0 is still just 0 plus 4 is 4. When I plug in a 0, y becomes a 4 and then I can plot that on a graph. That when x is 0, y is equal to 4. Let's try plugging in 2. 1/2 of 2 is 1, plus 4 is 5. We know this is a linear equation, so I can just plot other relationships without even having to plug them in my head. And I get this line, and this line describes how the lever of x is affecting y. And clearly it's making y increase as x increases. All right. So, one more question for you. Can we use variables to disguise mistakes in math? Well, here is a proof that 2 is equal to 1. And the proof is done with variables, and the variables here do disguise a mistake in a very clever way. So I want you to pause the video, look through this proof. It starts by saying, let's just assume that A is equal to B. Then it just manipulates them both, and they're able to prove that 2 is equal to 1 but there is a mistake in here. Let's see if you can find it. Okay, the mistake is right here, going from step 4 to step 5. So we can say the mistake is in step 5 when we divide both sides by a minus b. Well, if a is equal to b, then a minus b must be equal to 0. Anything minus itself is equal to 0. And when I divide by 0 to both sides, well, I'm just not allowed to do that. You cannot divide both sides by 0. And because we, in a very sneaky way, divided by 0, we were able to prove something that isn't true, that 2 is equal to 1. All right. So I'm going to put some more questions here for you to finish. And that is that for this lecture video. Have a good rest of your day.